I keep saying, you don't need biz dev if you've got good marketing. You don't need marketing if you've got good product. And you've got good product typically when you have very good technology and engineers, right? And product people.
One thing that, let's not do it now because I think the operative question is, what is Nillion? But I am curious to learn more about both of your experiences and what it was that each of you saw, right? What was it that attracted you to it, that made you think that there was something special here? Because I think every single person that encounters, whether it's Nillion or something else, has that kind of perspective. It would be an interesting story to plug. But Miguel, maybe you're the right person to ask this question to. The obvious big question is, what is Nillion? We know what it's not. It's not a blockchain. You've mentioned SMPC, Secure Multi-Party Computation, or MPC, Multi-Party Computation. It's a derivative of that, you could say, or it evolves from that class, but it's dramatically different in terms of its performance. So what is Nillion? Help us understand that, and especially given the fact that to the extent that the audience has familiarity with the space, they're going to be familiar with what is generally thought of as a public blockchain, right? A ledger that's public that you can audit. So what is Nillion? How is it different? And let's get into the meat of that conversation.
Sure. So I guess the main difference compared to a blockchain is that blockchains are focused on storage. They're focused on a number of nodes keeping the state, a consistent state on a ledger, which is a record with several transactions on it. And so it's not really meant for computations, although with Vitalik and smart contracts and so on, then it has evolved into the computational space as well. The difference is that Nillion was conceived as it's an evolution from secure multi-party computation. So it was conceived from the beginning as a compute layer, not just storage, but compute. And the other difference is that it's secure. So on a blockchain, typical blockchain, all the information is public. And so there's a restricted number of things you can do when everyone can see everything. So you can run the use case of digital assets, and that's fine, but you cannot run authentication. You cannot really authenticate against the network because your password would be completely public and exposed to everyone. Just one example of a computation that requires the concept of security. And so what Nillion is a secure compute layer. And that security means that the nodes can have information from the different dealers, from the users participating, but that information is really not available to them. They cannot see what they're holding, and they cannot see what they're processing, but nevertheless, they can process that information and compute the outcome of computations such as authentication. So I can authenticate against Nillion, where my face biometrics are somewhere there in the network, scattered across a multiplicity of nodes. And I can compare passwords, and I can compare location and device information, but none of that information is actually available to the nodes, and yet I'm able to perform that function.
And that's the name of the network, right? What Nillion actually means is a whole lot of nothing. And so what's stored on the network, we can get into that if you would like to at some point in time, is literally a whole lot of nothing. One other thing that's interesting is that Vitalik himself has said, I think numerous times, but there are several key quotes, that he believes, and Joe Lubin, the other founder of Ethereum, has said this as well, that the blockchain itself is well suited to become the kind of record layer, but it is likely that the heavier computational capabilities are taken off-chain somehow because they just weren't designed for that. And as decentralized computing becomes more and more prevalent in creating this ecosystem of Web3, that's just what's going to happen. So we are literally on the cutting edge of creating a fast, secure, decentralized computation network, which is really interesting. And that's also why I saw this as something that could be transformative. Like Miguel said, it isn't a layer one. It isn't a blockchain, right? It doesn't seek to order transactions. It seeks to do many, many other things which can help facilitate a decentralized world far beyond what we have currently with blockchain.
So SMPC is a peer-to-peer network, right? Normally, when you compute something, with SMPC, each participant has his or her own data. It isn't shared with that particular node or participant, and then a secret is shared as some information is computed, correct?
Yes, well, actually it can be implemented on top of a peer-to-peer network, but also on top of any other type of network. So it could be a network of authenticated nodes where each node knows to which one they're connecting, and those connections are fixed. But it can also be implemented on top of a peer-to-peer network, which is a kind of a decentralized approach. But the idea, as you mentioned, is yes, you're hiding the information that the nodes store, but yet you're able to compute.
So let's talk about that a second, because that was the thing that, going back to Andrew and Alex's experience of like what they found interesting, compelling, that's kind of what I found really compelling. The way in which data is not just computed, but stored hidden in the Nillion network. It's really fascinating. And I think it would be helpful to talk about examples of SMPC, because you can get an appreciation for the transformational processing capacity of Nillion versus SMPC. So let's say we're each nodes in a traditional SMPC network, right? You, me, Andrew, Alex, members of the audience. Let's say we have I don't know, 10, 20 of us in here, and we want to process something. We want to figure out some important piece of information. I don't know what. There's a classic millionaires problem that we talked about on the podcast, which is each person is worth a certain amount of money. We don't want to reveal how much we're worth, but we want to figure out where along the distribution we all are. But there's all sorts of things you can do. Give us some examples of practical things that you can do with SMPC that it's been used for, so that we can talk about how it works, and that'll give us an opportunity to talk about Nillion and truly why it's so transformational.
So typical applications that have been used before are, for example, signatures. So I have a private key that is the one that allows me to sign, let's say, a transaction. And so instead of having the private key locally in my device, what I do is I split it into pieces using SMPC and send one piece to each one of these nodes in such a way that the nodes don't really have anything. They cannot get back to the private key from the piece they have. And that's a property, mathematical property called information-theoretic security. And so, but yet I'm able to get them sign messages for me. So transactions, for instance, in that I take it as a transaction, I break it again into pieces, I send it to the nodes. Now each node has a piece of that transaction, and of the private key. And now the signing process comes, which is the processing in this example. You mentioned the millionaires problem. That's another processing. But think about as a programming language. You can type algorithms, and then you have the nodes execute those algorithms. But the thing is that in SMPC, in traditional SMPC, all of these algorithms that involve multiplications, multiplying stuff, they require the nodes to exchange messages. So I, as a node, have to send one message to each one of the other nodes in the network, and I have to receive a message from each one of the other nodes in the network per multiplication. So imagine if you're doing a lot of multiplications, that's a lot of time that gets lost in the communication between us. And that's the major problem with SMPC, because it really means that for very simple computations, it's already taking a lot of time, because that communication is very expensive. So that's why the only real applications of SMPC so far have been niche applications where the algorithm was very simple. Signatures is one example. Another one would be, I don't know, comparing things. Another one would be transferring messages from one blockchain to another. It has to be really simple, because otherwise SMPC doesn't scale. But what we're facing here is the possibility to do way more than that.
But how does it work that you're able to hide data without encrypting it?
So, good question. Encryption is just a form of information hiding that comes from part of cryptography that is based on computational theory. And so it's based on the fact that there are some problems which are very hard to solve. And you put the problem between the attacker and the information that you want to protect, so that the only way for them to get to the data is to hack or to solve this problem, which is very hard. But it's not the only way to create crypto. You can create cryptographic primitives from a different corner of maths that is called information theory. It was founded by Shannon in the 1940s. And the trick here is not to play with hardness, with the difficulty of a mathematical problem, but rather not to expose information to the attacker. So I'm going to do something with the information that deletes those traces of data and of information, and so that the attacker, even if they have an infinite computational power and quantum computers and whatnot, they cannot do anything with that message, with that encrypted message, because there is no information there to exploit, to harness. And that's how secure the technology behind Nillion is. That's what's called information-theoretic security.
So what are some examples of, again, because I do want to switch it to Nillion, but what are some examples of, or maybe you already answered this, of areas where SMPC is currently used in the real world?
Yes. Another example would be away from blockchains. It's been used, for example, in anti-money laundering, where you have different banks, each one knows something about their customers, but there's regulations preventing those banks to talk to each other, data protection, bank secrecy. And so they create an algorithm that is able to assess the risk in terms of money laundering based on the information that is available at both ends. And another example used in Estonia, which has been a pioneer in secure multi-party computation, is cross-referencing data. Like they found out that the computer science students were failing a lot, and they were thinking, is that because they're stupid, or is it because something else? So they cross-referenced that information with the tax records, just to make sure if they were working, and that was the reason why they were failing. And it was a computation that I think took hours and hours, because it was a large database, but in the end, they were able to cross-reference those two things and really figure out that indeed, they were not stupid, they were just working while they were studying.
Do you guys have anything you want to add to that?
Yeah, I mean, I think what's interesting is in the 80s, so computing was developed, all right? And immediately you kind of think to yourself, well, if everyone in this room has a computer, the basic problem is how do we create trust between each of the people in this room? Immediately, they came up with this theorem called secure multi-party computation so that we could all kind of compute data, sometimes depending on the flavor without us knowing what the data was, and get a result where if a certain percentage of all of us came up with the correct answer, then the resulting computation would be correct. That is what we call Byzantine fault. It actually underpins blockchain and decentralized computing in general, right? So SMPC then kind of developed this secure multi-party computation. And then from another stem of thinking was blockchain, which then kind of crystallized in 2008, or I think whenever the Satoshi Bitcoin white paper was written, so the proof of work algorithm, right, which solved a major problem, double spend problem, but it created basically what is essentially the blockchain era, right? But this other part of computation sort of has been there in the background. There are big businesses that have been built off it and use cases. So Fireblocks is an example of that, and some of the other examples that Miguel gave. And now we're reaching a convergence because what blockchain did was it created transactions. And that was like the frontal, the tip of the spear into the public consciousness of decentralized and distributed trust in computing, right? But as Miguel said, you started to append computations to an immutable ledger. Why would you do that, right? Why calculate computations in transactions per second? It doesn't so much make sense. And then, and then you have this SMPC technology, which when I saw it, it kind of occurred to me that this was almost like proof of work was to blockchain is what, Nil Message Compute is to SMPC. It's a way to compute where you don't have the restrictions of having to send many messages to each of the nodes. So we would never have to talk. We were all nodes in if every person in this room was all nodes in a decentralized permissionless network, we would never have to talk to each other for us to be able to come to an agreement to a computation, as long as we're doing, 2/3 were honest, that's right. And that's That's the Byzantine rule. And so, when I saw this, I was like, wow, this is a different way to look at decentralized computation, because for the first time ever, we have a permissionless, decentralized computation layer, which comes with the added benefit of what SMPC had, which is information-theoretic security, non-encryption, and computation, not order. So you're looking at value, not order. So you're not looking at transactions. And yet, from the blockchain side, we borrow permissionlessness and decentralized trust and tokens, if you like. Staking mechanisms, if you like. So it's really the merger of the two, creating something that, honestly, the world has never seen before. So,
I think what's really interesting about SMPC's history as well is that the privacy and the security of SMPC has been recognized in the uses that have been done. When you think about Estonia and their use and the amount of time it took them to compute on this data, or the way that Fireblocks uses it with these private keys as a method of security, that part of what SMPC is capable of has been recognized as a very valuable piece. It's that scalability issue and that computation part that has always been what's holding that technology back and not allowed it to grow in the same way that blockchain has. It hasn't been able to be the tip of the spear because you couldn't scale and you couldn't use it in a way that was effective because of all of the messaging that would take place. And to add to what Andrew was saying, NMC itself steals the asynchronous computation part from blockchain as well, where not all of the nodes have to be doing the same thing at the same time in order to complete a calculation. That's one of the improvements that NMC has added. So it is almost taking something that people recognize as this secure way and great way to either compare pieces of information or secure pieces of information, but it's been restricted by this problem with the messaging and the time that it takes to do computations, and freeing it from that. And that's what we're seeing here with Nillion. So
yeah, I just want to emphasize something on the point about information-theoretic security. What's also relevant is, again, to the point about how Nillion hides data, the distinctions between that and encryption. That's central to how Nillion is able to compute data while it remains private. And that opens up a whole range of use cases that currently aren't available. That's what excited me so much, whether it's computing genomic data, private health data, data that's highly regulated by governments, where regulation doesn't allow us to service those use cases. Other simple examples, like if you have an airline manifest list and you want to run it against a terrorist database. Right now, if you're going to do that, you expose all that information. But if you have a network like this, you can actually say, I want to see if any of these passengers on all of these flights are on a terrorist database. That's all I want to know. I want to know nothing else. I don't want to know their names, their heights, where they were born, nothing else. And that, in particular, is what excites me. Of course, all the points about off-chain computation, interoperability, all that stuff is super useful. So let's talk about NMC and the distinction between what we've just talked about and how you guys manage to eliminate the need for internode messaging, because this is what's so fascinating.
Yeah, that's actually the key of the issue. Well, in secure multi-party computation, you're typically relying on one building block, which is a cryptographic primitive. And you're asking of this primitive a lot of things, because it has to be correct, which means it has to run the computation in a distributed way, and then it has to give the right result when the nodes send their results back for reconstruction. But it also has to be ITS, as you said, information-theoretic secure, and it also has to operate in the presence of bad actors. Just 3 things, 1 primitive. That's a lot. And so the idea with NMC is to actually divide and conquer and say, we're going to distribute those 3 things, but among or between 2 different primitives. And in doing so, we're going to get more degrees of freedom to design those 2 primitives. And so there's primitive number 1, which is linear secret sharing. It's just about the mechanism to share secrets with a number of nodes. And we're going to use that to hide randomness, some randomness that we will call blinding factors. So with this primitive, we're going to take care of the nature of operating in an environment where some actors are bad. That's assigned to this primitive, linear secret sharing. Now the other primitive, because it doesn't need to deal with that problem, we get more degrees of freedom to really design it for efficient computing. And to do that in such a way that the nodes don't need to communicate to run an algorithm. And that's a primitive called one-time masking. And now the next thing that we ask of the two is that both need to be ITS. It's like if you're having two Lego pieces and you want to put one on top of the other one, but at the interface, it needs to be ITS because otherwise the connection of the two blocks wouldn't be ITS. So if you want information-theoretic security as a whole, you need each one of them to be ITS. And in so doing this combination, the way it works is that if I have a secret now, what I'll do is take from the network the pieces to reconstruct the randomness using the linear secret sharing, and then I'll use that randomness to mask the information from my data. I will get a particle, which is what is ITS, and then I'll send that particle back to the network. And now that particle represents my data, but doesn't really have any traces of it, and you can operate with it as if you were operating with the secrets directly. If you want to add secrets, you add particles. You want to multiply them, you multiply particles. And that's the way the two primitives are connected together.
So normally, let's say if you're using Samir secret sharing, the secret is embedded. The secret is embedded inside of a polynomial, but it's hidden through LSS directly.
Exactly.
Whereas what Nillion does is it combines a one-time mask with LSS, with SSS variants of it, and you use LSS to hide the shares of the blinding factor. And then once the information is masked, the individual nodes can compute it independently without actually knowing what it is. So you take the most essential part of that operation, which is the least computationally intensive, which is the blinding factors, and that's where you use LSS, and then the rest is basically...
Exactly, because the problem was that LSS, if you want to use it directly on the secrets, on the information, it works for additions, but it doesn't work for multiplications. Then is where you need the communication between the nodes. And so rather than trying to square the circle, we just use LSS for just storing the blinding factors, not doing any operation with them, just storing them. But the operations, we do them with the other primitives.
Can I actually think, how do you, because like in some ways, if you explain it correctly, it seems kind of simple, right? But how do you come up with something like that that seems superficially so simple, but which is such a breakthrough in terms of performance?
Well, there's no easy answer for that, rather than by searching a lot of possibilities. And by searching possibilities which are not evident, because there's very smart people who have thought during 30 years about this problem. And so obviously the solution is not going to be a mild tweak that you do to linear secret sharing, like Samir secret sharing, or some minor modification. It's going to be something different. And so in testing completely different and new ideas is where you actually have a higher chance at hitting the right one.
I just want to say, if anyone, I don't know if at this point, if anyone has any questions and you want to pass the mic around, I can't really see anything because we have a bunch of lights here. Looks like we have one question here. We're just going to need to get a mic to Jared here.
Well, while they're doing that, I do want to point out it is an important distinction that when you have particles that have been masked and are in ITS, one of the foundational and amazing things about NMC is that we can run calculations against that information while it's in that secured form. When you think about encrypted information, you have to decrypt that information, then run an algorithm or calculation or whatever you want to do, and then encrypt it again. In terms of computational capacity, the requirements for it, and the time that it takes to do that, and where it is as a technology, it's nowhere near where ITS is in terms of being able to run calculations on secured information. And that's a fundamental part of what makes Nillion so powerful, is that we do have that ability to take a piece of information. It is never revealed, yet we can use it in any way that we want in any computation that we want.
It's funny because a lot of people talk about that, when they refer to Nillion, this information-theoretic secure element of Nillion. But it almost comes for free as part of the creation of a computation layer. So we were objective, create computation layer without the restraints of blockchain, but because of the way that you achieve it, you get a secure computation layer. I mean, it's information theoretic secure. It's not even encrypted secure, right? It's a unconditional security secure. So, what that does is it opens up a whole bunch of really interesting use cases that weren't evident or weren't possible with blockchain. Not just from the fact that you're doing different types of, using a decentralized network in a different way, focusing it on computation, but also, the fact that it's information-theoretic secure.
So, and I want to talk about use cases, guys. Let's see, right there, Jared. Jared from Yahoo Finance.
Hi there, Jared Blakely. I'm really glad you guys are saying decentralized computing and you're not just broadcasting DeFi. So I'd just begin with that. Two questions. One relates to what you were just talking about. The other is kind of big picture. I don't know if we have time, but so what you were just talking about, you're sending these particles kind of like broadcasting. How does it scale, and how do the receivers not get lost in the volume as the messaging volume picks up?
So there's just messaging during two phases. The phase where you kind of distribute your particles, but that takes place in parallel. And then the phase when the computation has finished without communication, and there is a particle that represents the output of that computation held by each one of the nodes, and they send those particles over to whatever node has been designated as the node which gets to reconstruct the result. And so, how does that match against the scalability, where it doesn't affect computation because computations take place without any message exchange, and it slightly affects those two initial and final phases because the more nodes you have, the more messages you send, but those takes place in parallel, so it doesn't affect them, that much. And the only thing that would be affected then is the cost of storage, because the more nodes you have, the more nodes that will need to have, to store those particles, and that will have an impact on the cost, essentially, of storage for the network. But essentially, you can scale in number of nodes, which gives you more security, at no price to be paid regarding the cost of computation, and that is the key element. We've broken that, magic or that connection that's always been there between the price of computation and the security.
I think it's important as well to note your mobile phone can send out hundreds of messages simultaneously, and this is just a mobile phone, right? Without experiencing a degradation in speed. Or infinitesimal degradation in speed.
Yeah, and actually, when you load a website, there's connections in parallel coming to you, lots of them. So it's no big impact.
So I have a query, right? I send it out. I split it up, send it out to the network. It sends me back. Let's say I'm the result node. I want it sent back to me as opposed to you, right? It sends it back to me. That's one message there, the compute, and then one message back. But it's sending it to a bunch of nodes in order to get that decentralized secure aspect, right? And that there is almost as fast as client server. That's why.
Yeah, I think I misunderstood, maybe thinking that every node had to receive all the information and do the calculation, which doesn't appear to be the case, right?
Yes, it is the case because you want to have many nodes do the computation in parallel, so that you can be resistant against the possibility that some of them are bad actors. That is the reason why you want to kind of do this in parallel with many nodes, but because they don't have to communicate, they act as if it was just one node doing the computation. They're as fast as one node.
Are you asking Jared for the amount of time it takes to spread all of the data across the network of nodes?
I guess basically, is this n log n, or what is it? What's the computational complexity?
So the computational complexity is the one that you would have in plain text. There is no difference. If your original algorithm runs in ON, so will it run in this private form. And if it's ON squared, then it will be ON squared.
Is there any kind of computational complexity related to the blinding factors?
No, it's very simple. It's ON, essentially. It's a very simple operation. It's linear algebra, and it scales with the number of particles that you're creating.
So the second question is a little bit more big picture. In the U.S., we have the Securities and Exchange Commission, various regulatory agencies. I think Gary Gensler at the SEC, probably the most aggressive. I think putting the U.S. at a disadvantage when it comes to decentralized computing. I understand why they're putting the brakes on certain DeFi projects because they feel like old kind of schemes rehash, or it's just kind of bringing crypto into the mainstream reality of finance. But I'm just wondering, I understand your product is very, very different. Do you see any kind of regulations in the US coming down the pike that could really stymie what you're trying to do in a decentralized computing network?
This is probably a question for Andrew or Alex.
Yeah, if you have something.
So I feel like yes, firstly, I see that coming for sure, right? Given the size of the network, the fact that, you could be transacting on a DeFi network with terrorists, for example, and, people are definitely looking at this. So one part of this network, so let me address two parts. The first is one of the possible early use cases that we have envisioned is decentralized KYC. Why? Because you can store your identity in a network which doesn't store anything. It's literally information-theoretic secure. It's Nillion. It's a whole bunch of nothing, right? It's provably, mathematically provable that, that there isn't a trace of your identity on the network. It's not like you've hashed your identity or it's an encrypted file or something like that. And that then can form the foundation of what I think is decentralized KYC, which is really interesting to me. Thus, decentralized KYC, where you as the individual hold the right to that identity, can remove it because it's not an immutable ledger. So therefore, you have the right to be forgotten, right? So thus being GDPR compliant, right? And yet never having a trace of your actual identity on the network. Also allowing you to prove who you are to a potential government without even it doesn't have to be a government, it could be a bank or some sort of regulated entity, without ever having even to show them the data on the network. It could do a compare function without ever having to do that. So that's the first. I actually think that that's actually the way that this is all going to go, especially as crypto becomes more and more prevalent. And the second is, as I mentioned, this is a GDPR compliant solution. It's something that in 2019, when Miguel came to me, they said, we think that identity will one day come onto a global network. I think that's correct, but I don't think you do that as a frontal motive. I think you need a GDPR compliant solution. You can't just have hashed identities or encrypted identities. I think you need something like this that has the right to be forgotten, and where you can't just steal a bunch of encrypted identities and then put them away until the invention of higher levels of computing power, which is what some criminal organizations do, or perhaps governments do it as well. In this situation, you have something where that information is ITS, doesn't leak any information. You have the right to be forgotten, and thus you have a GDPR compliant solution. So my intention with this is to sort of go where the puck is going, because I do believe that is going to be a hot narrative in future.
I think what's really interesting about that use case as well is that it is a way of providing identity and decentralized identity, and what these DeFi platforms are going to need as regulation comes down the pipe, but still speaks to the true nature and I guess the underlying idea of decentralized identity, where they don't have to go out and collect this information from like a normal KYC, individual or company that does that specifically, and then you can store it in a way where they can ask those questions that they want. They can get that information they need to be able to comply with whatever rules are in their jurisdiction, but they also don't have to be, Uniswap doesn't have to collect everybody's passport and banking information, right? It can be in a place where they just can be sure that you're not this person or don't live in this country, and then everything else they don't have to collect, and they don't have to be one of those big data aggregators now and be regulated in the same way as a bank.
Something interesting about that solution as well. It isn't something we're trying to build. It comes free with what we need to build for the network. This is something I realize this is the first time I've said this publicly, but the founding engineer of Uber joined us as our CTO. And as I was discussing with him, the engineering pathway of Nillion, we were sort of talking. We were like, well, at a base level, we're going to need to authenticate who you are in order to get to the data that you're putting on the network, right? So let's think about this. If I need to authenticate who you are, how do I do that on an Ethereum ledger? I do that with a private key, but that's a simple compare function of, does the public key match the private key? But with a Nillion network, what you can do is have several layers of authentication. It could be a public key, a private key. It could be a password. It could be a matching of this side of your face or of the vectors in your face. It could be a fingerprint. It could be a multi-sig authentication, which is more like what Fireblocks uses SMPC for. You're talking about a network that can authenticate using several factors where it never actually has to, and were you to store a private key in there, it would never have to reveal the private key. You could just create signed transactions and put it onto another blockchain, right? This is the power of having a computation layer built on SMPC, or rather NMC, right? Nil Message Compute, rather than blockchain or SMPC. So you get that identity use case almost for free. Thing is, I hate talking about identity use cases because the graveyard of identity blockchain projects is long, and it will continue to be filled with tons and tons of projects. I did a lot of research out of respect for the innovation that I saw out of Miguel a couple of years ago. I did a lot of research, and the only way you can attack decentralized identity and thus decentralized compliance, what I found is to look at countries, like Brazil in the case of Unico, or the Temasek organization in terms of Singapore, and see how identities have actually been put on centralized servers where 70% plus of the population is actually on a single database. And that's always been by way of providing a use case. So in the case of Brazil, it was fraud detection. For Singapore, it was passport verification. But you need to provide a use case. You can't just say, hey, everyone, your identity is going to be on a decentralized network now, come upload to us. That will never work. So I don't like talking about identity use cases, but it is central to your question because that is where the compliant angles of decentralization and of government are going to go.
Andrew almost went there, but to expand on it too, when we're talking about these authentication methods that we could use, whether it's the fingerprint or a biometric or voice recognition, or you could do something as crazy as iris or even DNA as an authentication method. Not saying we're going to build any of those things, but it is possible. All of those pieces that would authenticate you, whether it's that picture or biometric that is on the network, or it's that voice that you're matching against, all of that is masked and stored in ITS in a way where none of the nodes that are doing that authentication of you through biometric or voice or what have you, they can't see any of those pieces of information either. So when Andrew's talking about Unico in Brazil, they're fighting the online fraud by using biometrics and a piece of identity to fight the e-commerce fraud, but they're holding those biometrics and those IDs on their centralized encrypted database. So they have a picture of a face matched to an ID for 70% of the population of Brazil, right? That is a massive amount of people that you have very sensitive information on that one company now controls. With Nillion, we could do the exact same thing on authentication with a wide range of multi-factor authentication methods, and none of them are on our network. The nodes don't know anything about you. They don't know what your face is. They don't know what your voice sounds like. All that information is dispersed in a way where, in reality, you're the person that controls it, and none of the parties involved in actually recognizing that that's you when you're logging in or authenticating yourself. None of the parties out there that are doing that authentication know anything about you.
And yet, once you have that piece of data on the network, even though it resembles nothing, it can then be used at your request for every other potential use case. Decentralized LastPass, the KYC one we just said, a Fireblock solution, the biometric data that Dimitri had said, or storing your private key by way of hiding it by way of your biometric password, two-factor authentication, et cetera, et cetera. So it scales naturally through this hidden data, because that hidden data is useful for many other potential use cases.
I think the decentralized LastPass is a great example to think about, because it's one of those things where everyone has experience using something like that, or Apple's keychain, And you always kind of wonder, well, where are the keys stored? Like, how secure are they really? Because ultimately, they're secured on a centralized database. So how would, and I see, by the way, that we have a question back there. We're going to go to you in a second. But how would something like that work with Nillion? And how would it be tangibly, materially, meaningfully more secure?
So, it's funny because you have this, I have money on an Ethereum network. It's a decentralized network secured by a decentralized network. And I take this private key. I don't know where you guys put it, but apparently you're supposed to put it, a best-in-class solution, have a piece of hardware, a hardware wallet that has a seed phrase, put that seed phrase in a fire-retardant envelope in a safe somewhere. It's still centralized, right? It's still... It's super stressful too, like extremely stressful, Or hide it in your LastPass, still a centralized server, still all centralized points of failure, right? It doesn't really make sense. So with Nillion, what we want to do is to create a permissionless network, which is ITS, which can, as one of the use cases, store a private key and even not allow the reconstruction of the private key. All it does is it just reconstructs signed transactions onto blockchains so that once you authenticate, you tell it what to do, you never get the private key back. All you do is tell blockchains what do you want them to do with their money, right? That's a cool concept. Because then the way you authenticate is, let's say for me personally, I would do, a biometric, a password, right? And then I'd probably do, if it was a lot of money, I'd probably do a two-factor authentication and maybe a multi-factor authentication. All programmable in the network, right? Doesn't rely on me having a private key. And then I can tell the Nillion network to tell the Ethereum network to send that Ethereum or that USDC somewhere else, et cetera, right? That to me is a super cool potential use case where you finally decentralize the whole lot.
Yeah, and this isn't a theoretical thing. And nor is it isolated to crypto. Data integrity and authentication are like central to the future of the internet. Today, right? Like hacks and data integrity issues are like huge. Simple examples that we've talked about on the show are easy hacks. You could hack the blood record database at a hospital and people could just start dying on tables. These are actually like theoretical attacks that people consider mounting. So there are all sorts of ways in which this is relevant. There's someone back there who has a question to ask.
Does this work? Hi, it's Jesse Ash, Greener Media. Congratulations, guys, on launching this. And I mean, the math and science, I'm a filmmaker, so it's way above my head. But Miguel, you talk a lot about bad actors and adversaries. What's keeping each of you guys up at night? Is it the ghost of Goldman Sachs past? Is it, is it authoritarian regimes that are going to bring you down? What's the biggest adversary that you see in terms of taking this?
Yeah, a very good question. In terms of security, because I guess your question is about security, you have many different layers that you need to take care of. So you would have the network layer and the storage layer. They are susceptible to a number of attacks, but then again, it's well known what kind of things you can do to prevent that from happening. Then the core of the network itself, which is where you have the bad actors, the nodes which deviate from the protocol and try to do something else. That's also okay because you can work with the numbers that Andrew was referring to. You can design the network in a way so that this type of attack is really hard. The maths, okay, no problem there. The problem that I have is at the client level. So front door attacks, because that's before even you're touching Nillion's logic, Nillion's code, that you may have a virus in your computer, malware, someone may be watching over your shoulder and take the secret out of you before you even particleize it and send it over to the network. That kind of attack is very hard to address. You can always harden the mobile application or the device where you deliver Nillion's SDK and the code. And one thing you can do is to use trusted execution environments, which is a hardware area of the mobile phone, which is secure. And it can also even have access to the user interface. And it's a completely separate area from the rest of the hardware that is accessible through other programs. but there's no silver bullet here. And so that's one thing that, or the most, the thing that worries me the most.
Yeah, I mean, and Miguel brought it up, and it's very similar for me. I mean, I'm CEO. A lot of things keep me up at night, but I think the idea of the yeah, I know, so that you can sleep well. The idea that the device that the dealer node is using can be compromised. And thinking back to, in September of 2021, about 6 months ago, when Apple sent out an update to finally take care of the Pegasus exploit. If you guys know what Pegasus was, it was a software that was developed by an Israeli defense contractor, where they basically found a way to break into your iPhone. And Apple had, for a long time, I remember back in, I think it was 2016, when the government asked Apple to build a backdoor into their encryption, and they refused to do so because they said it was so hardened that we don't want to build a backdoor because then that's going to allow all these people to exploit it. And it turns out somebody had for years and been selling it to state governments. And that software is watching what you were doing on your phone. And so if you're interacting with the Nillion network and Pegasus software was on there, then there could be somebody watching the secret that you were putting onto the network. And it's that point which is the part that really concerns me, and how we structure all of this properly, and what we can do for users to make sure that they are in a very secure environment when they're using it, because Apple, of all people, was hacked by this software Pegasus that was being sold to governments, and it was just, I don't know, 6 months ago that they finally put in a patch in place to prevent that from happening. So that's where a lot of the concern is what happens on the devices that are outside of the network. There's nothing that a software like Pegasus could do to get onto our network because of the authentication issues they would face, but on the device, they could see what that secret was.
Okay, there's someone over here with a question.
Hey, I'm Josh Ogle. So first off, I just want to say it was a fantastic presentation that you guys gave. These are really great answers. All three of you guys are clearly clever folks, and I've been following the things that Andrew Masanto has been doing for the past decade, and I can attest to the fact that generally he's well ahead of where I am, and I consider myself to be well ahead of a fair number of people. That said, where I'm not ahead is I'm very lay. I have a very lay understanding of certain technologists, things behind the technology and the math, and so I appreciate you guys presenting that in a way that's understandable. So that said, apologies if this is a self-evident answer, but my question is, these nodes that you're talking about that are doing this authentication, who are these nodes? And if they're not you, which maybe they are, but if they're not you, then what is the incentive or the motivation for someone to be having a node on your system?
Well, I mean, so we are building a permissionless network, and so anybody could be a node in terms of how we have the structure of. There's essentially going to be two different types of nodes. There's going to be light nodes and there's going to be full nodes. Light nodes are the holders of particles and can hold as many particles as they want. They participate in calculations. And we're going to have full nodes, which are going to be governed by what we call a DAO support score and a node health score that is going to look at the activities and the behavior of those nodes and other factors to decide which nodes can be full nodes on the network. So in terms of who can be a node, anyone can be a light node. Who's going to be a full node? It's going to be the really good actors that are known and that are supported by the decentralized network. And as part of the way that we are thinking about the construction here and the tokenomics of the project, we are going to use staking as a mechanism to align incentives. In order to participate on the network as a node, you will have to stake, and you are putting those tokens at risk depending on the behaviors that you take. One really great thing about the way that the mathematics and the construction of the network works is that we can see who is being a bad actor on the network. So when we're talking about with Miguel and was talking about error correction, and if there's one node in a calculation that comes back and says, forget it, I'm sending the wrong result, in that error correction, we can identify which of the nodes was the bad actor in there and can take action against them to preserve the integrity of the network. On top of that, there is an incentive structure for nodes that are on the network where they will receive compensation in order to run a node. So to undertake calculations, to store blinding factors, to store particles, there will be an incentive structure that is built around that so that people that are using the network will need to pay with nil token or something similar in order to participate in the network and incentivize the node to run the calculations, and they'll receive those tokens as payment for the time that they spend on running calculations or storing data, what have you.
And just to be super clear, so to be a full node, then you would need to go through some sort of authentication or like verification with you guys, or would this be based on scores that were approved over time?
I think initially, perhaps, right, as we bootstrap the network, but over time, the scores will be down to how much you're staking, what your availability is like, how many times you've been flagged for issues on error correction, etc. The DAO will determine that in the best interest of the network. Does that make sense? So I think maybe we'd maybe bootstrap it like that, but over time, I don't see that being an issue. In fact, I actually think that sometimes that you may want to dox yourself as a full node because it just leads to there's no other reason to remain anonymous, in that network. But yeah.
The issue at hand is a Sybil attack, right? A single node or entity actually owning many different nodes, perhaps a large portion of the network, and doing with that whatever they want. And so to prevent that, as Andrew says, at the beginning, when we don't have many nodes, then you need to maybe add this layer of authenticating the nodes, do some enrollment. But eventually, when the network is large enough, then that won't matter because it would be economically unfeasible for anyone to own a large proportion enough of nodes to do any harm.
It's like Ethereum staking, right? Like, now Ethereum's got such a huge market cap, it would be quite difficult to get enough Ethereum to be able to affect its validation under a proof of stake system.
That's exactly what I was asking, because Binance Smart Chain, each 21 validators staking, but they did verification ahead of time to make sure that they were.
Yeah.
In the white paper, it states that there's two groups of nodes, the T+1 nodes and then the rest of the nodes. How would the network resolve like node failure? Not necessarily malicious nodes, but how does the network resolve node failure, and how does that affect computation between the two groups of nodes, right? If a T+1 node fails versus another node. And do these nodes know which group they're in?
So essentially, the way to prepare the network against this type of failure, which is not malicious in nature, is to add redundancy. So to improve the high availability of the network, the particles are replicated across multiple nodes, and so are the shares. So that if one node goes down with a share, that share will be available from another node that has the same copy. And then regarding the two groups, there's actually a logical separation that has no consequences because in essence, T+1 is a parameter, a design parameter for the network. It tells you the amount of shares that you need to be able to reconstruct a blinding factor. And it doesn't matter if it comes from this set of T+1 nodes or from this set of T+1 nodes. What matters is the number itself. So it's really, there's no need for a node to belong to a group or to another one in that sense.
Hey everyone, I'm Grant. Thanks guys for these answers. It's been really helpful. One thing that just kind of popped to mind is you see the runway for what this can change. You get really excited, but I think one thing that I'm curious about, and maybe this is too far down the line, but when you look at kind of the current state of affairs with just people understanding technology and just overall, whether it's congressional hearings, whatever it may be, something that I'm curious about is how are you guys thinking about the overall approach of getting people to understand, a layperson that really has no technical understanding, how do they get up to speed on how transformative this is?
I think that, firstly, we've been given a gift because of this crypto boom and the fact that people are interested. But I genuinely think that eventually it's going to come down to utility and use and not to the technology. The technology is super cool. I keep saying, you don't need biz dev if you've got good marketing. You don't need marketing if you've got good product. And you've got good product typically when you have very good technology and engineers, right? And product people, And so I'm focused in this protocol much less on getting people excited. And people are getting excited about the technology, but I want the engineers and the product people because I want to create products that people end up using, you know? And that's really the focus. So I appreciate and I love the fact that so many people, and you guys are like the earliest in the space right now to discover this new paradigm of thinking. I appreciate that technological bit, but I think that, you know, the broader audience taking it to this general public that you are referring to is going to happen on the product level. And this is honestly, Conrad, when he first looked at this, the CTO who literally built Uber he was Garrett's roommate in college. He said to me, you know, we have to focus on product here. This technology, well, he read the technology. He's like, this is super cool. The physics is amazing, etc. It's getting the right people interested, right? But then we need engineers and product people to be able to make that into a layer which we can build products on top of, which excite other people. And that is also why, within the way that I built this, if I think about the way I built the other protocols, the mistakes I made were that I was so focused on the technology. God, Hedera was a cool technology, but I didn't focus on the ecosystem and on the resulting product. And that's why, as part of our founding team, a lot of the compensation of the people on the founding team is to do with the products that eventually get built off it, as opposed to just the expression of the technology itself, if that makes sense. So, you know, it will be a factor of education about that, you know, and a simpler narrative as to how to express the coolness of this technology. And, you know, the contrarian narratives get people excited. But when it comes down to it, you know, to hit something where we actually, you know, make a dent in the universe or potentially change the world, we have to create good products, and that's kind of the focus.
And it is embedded in the DNA of our project that we are building an ecosystem around this. I see Nillion as really an infrastructure layer that we're building out, whether it's in the meta layer to help with blockchain or into the real world in terms of the use cases there. But like Andrew said, we have these entrepreneurs that are embedded within our team that are going to go out and build products for this, but we're also building an entire ecosystem of bringing in what we call founding entrepreneurs and educating them on Nillion and then helping them develop products as well, because it's not going to be Nillion as an entity going out to, say, like major banks and selling an ALM product. It's going to be a founding entrepreneur who has built something that they're selling that uses Nillion as its backend in its infrastructure. And so we are really focused on identifying those people. We've brought many of them in early as part of the founding team, but at the same time, that ecosystem is where those products are going to come from that I think a lot of consumers or businesses or other people are going to interact with that are built with Nillion being the layer beneath them.
So I'm hearing a lot of products that you're going to be selling. I'm hearing a lot about test cases. Then I just heard something about public utility. So are you going to make money? Is the objective for you to make money out of this project, or are you going to be public good? Just trying to understand how you guys are thinking in terms of a company and a profitable company going forward.
So we are just building the base layer, and we are incentivizing people to build off the network. The entrepreneurs who build off the network, they keep all that equity for themselves. Right? They can build for profit or not for profit. It's up to them. We want to be a pure Web3 company with the understanding that, or Web3 public utility, with the understanding as the founders who are building this, that we need to encourage the first use cases because, as I said before in answering the other question, as you get more use and data into the network, it becomes more and more valuable. So I see it working at some point in time more like the Ethereum Foundation.
Hello, my name is Sage DeLeos-Young. I was just wondering, because Nillion is a computing platform that computes using secrets, right? So I'm wondering, after the computing has been resolved and been done, and we have like that new data point, does that go on the blockchain itself, or are these secrets coming from the blockchain? Or like, where do these secrets come from, and like, what happens after these secrets are used? Like, where does the product of those secrets like go to?
Is that generally a question about where is the data stored?
More, like, kind of yes, but more just like, where does the data travel after the computing is done? You know, like, it's a convergence between blockchain and a computing platform. So like, where does that convergence mean?
So there are different configurations. In one configuration, you can think about Nillion as being an off-chain layer because it's not a blockchain itself. And so in that configuration, the data could go back to the blockchain. But generally, because Nillion has its own consensus mechanism, which doesn't even require messages to be exchanged, it can live in and of itself, on its own. You can just finish the computation, deliver it to whomever wants to consume it, and that's the end of it. You don't need to really rely on a blockchain underneath to be able to do some kind of settlement or to leave some audit trails, because Nillion is able and capable of doing that on itself.
If you wanted to, you could. Yeah, totally. And that's what Vitalik said, right? Use Ethereum as the settlement layer, and that's a great use of a blockchain. But you can see how it's a different layer. It's kind of a metal layer, if you like, So, yeah.
Yes. Hey guys, JP. Thanks for the great talk. Really impressive. Is there a simple explanation for how the particles can be processed while separated without any node interaction? I'm just struggling to wrap my head around that. How the particles can be processed while separated without any node interaction.
Yeah. In essence, a particle is the result from applying to a secret blinding factor, a set of blinding factors. So you can think of it as being a multiplication. So essentially, because the multiplication is commutative, you can multiply particles, and that would leave you the multiplication of the secrets and some multiplication of blinding factors. Now, the next operation you want to be doing is addition. So you want to prepare things, the blinding factors, in such a way that once you've multiplied them, all the blinding factors kind of cancel each other out and disappear, and then you just have the multiplied secrets that you can add then later on. So in essence, the idea is, okay, let's add some blinding factors to the data so that the data is protected. But those blinding factors are going to disappear as you operate that data, as you compute on that data, so that they are removed, and what you end up with is the multiplication and addition of the secrets, which is the actual result from the computation that you want. You would really need to look into the maths to get a grasp of it, but that's kind of the high-level idea.
We had, by the way, the University of London Royal Holloway, a professor, look at the mathematics, and she came back and said, this is really, really innovative, and ended up joining our team. So that was my due diligence of the math, because I had the exact same questions as you. I'm not really a math brain either. I'm pretty good, but not that good.
My monkey brain's like having trouble.
I have monkey brain too. Yeah. I want it to be a story of like this community that sees the potential, these founding entrepreneurs and parts of the founding team that are really enthusiastic about potentially building off it, and where they actually, they're talking to Conrad, our engineers, as almost like product leads. They're like, hey, I need this to happen. Look at the way I need to construct data in order to make this use case happen, right? So that what's happening is at the 6 to 18-month period, you've got these use cases happening. Now, as you get to the 24-month period, what I want is for one, ideally, but hopefully more, but one use case to start really catching fire, whether it's KYC, the decentralized KYC, or decentralized LastPass, identity biometrics, interoperability, private NFTs, private smart contract. It doesn't matter to me, right? If one propagates, then the fact that you're using our network to authenticate will propagate the other use cases, will help the other use cases. And then that's when an Ethereum-like effect happens, and hopefully within 24 months, you start having these really interesting use cases pop up all over the network, and then it becomes this global network of nothing, which literally holds everything to do with whether it's identity or passwords or whatever. It's a very contrarian narrative, right? Store your secrets in plain sight. It makes me feel like when someone first told me internet money, like that was really weird to me. But I want those contrarian narratives, and I think that is a possibility for what happens in 24 months.